Welcome back to Anseli. Learn while you fall asleep. There are no ads on this channel, ever. Just calm, uninterrupted learning while you rest. Tonight, we are covering the Northern Lights. If there is a topic you would like us to make next, leave it in the comments. We read them all, and we will create it for you. The room is very quiet now. You can feel the weight of the blanket resting across your shoulders, the way it settles into place without effort. The pillow has found its shape beneath your head. Your breathing has slowed, all on its own, the way it does when the day releases you. There is nothing left to do, nothing left to solve. The world outside continues without you for a while, and that is perfectly fine. And as the quiet deepens, let your mind wander north, very gently north, to a place where the sky sometimes moves in ways that seem impossible, where curtains of light appear in the darkness, green and violet and pale rose, shifting across the stars like breath made visible. The Northern Lights. They have been there, in the Arctic skies, for as long as there have been skies to watch. Long before anyone understood them. Long before the words existed to explain what they were. The Sami people, who lived in the far north of Scandinavia, saw them on winter nights. They had many names for the lights, and many stories. Some said the lights were the spirits of the dead, dancing. Others said they were reflections from vast schools of herring swimming beneath the ice. The lights moved like something alive, and so it seemed natural to imagine life within them. The reindeer herders would see them while traveling across the snow. Long journeys in winter darkness, following paths they knew by heart. The aurora would appear above them, casting a faint glow across the landscape. Just enough light to see by. Just enough to feel accompanied. Oh, there was comfort in the light. A sense that the darkness was not empty. That something beautiful could happen in the coldest months, when the sun had gone away. The herders moved slowly through the landscape, their reindeer finding paths through the snow that seemed invisible to human eyes. The animals knew the way by instinct, by memory, passed down through generations. And above them, the sky would sometimes bloom with color. Green, mostly. A soft, pale green that seemed to glow from within, like ice lit from below. The color would start as a faint band on the horizon, easy to miss if you were not paying attention. But then it would grow. It would spread. It would rise up into the dome of the sky and begin to move. The movement was slow at first, a gentle rippling, like a curtain stirred by a breeze. Then faster. The light would fold and unfold, forming shapes that lasted only seconds before dissolving into new shapes. Arcs and spirals and rays. Patterns that seemed almost deliberate, almost intentional, but were not. In Finland, they were called revontulet, foxfires. There was a story about an Arctic fox running across the snow, its tail sweeping up flurries that caught the light of the moon and scattered into the sky. A beautiful image, a gentle one. The kind of story you tell a child who asks why the sky is glowing. The story made sense in its own way. Foxes were clever, mysterious animals. They moved at night. They left tracks that appeared and disappeared. And the aurora did look like something in motion, something fleeting and wild. The Finnish people, who lived near the Arctic Circle, grew up with these stories. They learned them from their grandparents, who had learned them from their grandparents, reaching back through time to a point where no one could remember when the story began. It was simply there, part of the culture, part of the way people understood the world. The Inuit, far to the west across the frozen sea, also watched the lights. They saw them as torches, held by spirits guiding the dead to the next world. On very cold nights, when the lights were bright, you could hear them if you listened carefully. A soft crackling, like distant fire. A whisper. Some Inuit groups believed you could summon the lights by whistling. Others believed you should stay silent, show respect. The lights were powerful. They deserved caution. Children were sometimes told not to wave at the aurora, not to draw its attention. The lights might come down and take you away. Not in a frightening way exactly, but in a way that meant you would not return. These were not superstitions. Not really. They were ways of teaching respect for forces beyond human control. Ways of acknowledging that the world was larger and stranger than it appeared. That there were things in the sky and the sea and the ice that could not be fully understood, only observed and honored. For thousands of years, this was how people understood the aurora. Through story, through the language of spirits and animals and ancestors. Not because they lacked curiosity, but because the lights felt like something beyond the ordinary world, something sacred. And in a way, they were right. The aurora was beyond the ordinary. It came from farther away than anyone imagined. It involved forces that had no names yet. It connected the earth to the sun in ways that would take centuries to understand. But the stories were true in their own way. The lights were a bridge between worlds, just not the worlds people thought. The first person to write about the northern lights in a way that survives today was a Greek named Aristotle. He lived in the 4th century before the Common Era, in a world of olive groves and marble temples, far from the Arctic. But travelers brought him stories. They described lights in the northern sky, flickering like flames. Aristotle thought carefully about this. He believed the lights were made of vapors rising from the earth, catching fire in the upper air. He called them chasmata, chasms, because they seemed to open in the sky. It was a reasonable guess, given what he knew. Fire was mysterious. Air was mysterious. The sky was very far away. He wrote about other lights too. Comets, meteors, phenomena that appeared and disappeared without warning. He grouped them all together as atmospheric events. Things that happened in the realm between Earth and stars. For more than 2,000 years, this explanation lingered. Vapors, combustion, something burning, high above the world. But the lights themselves did not care what anyone thought. They continued to appear, patient and silent in the long Arctic nights. In medieval Europe, when the aurora appeared far enough south to be seen, it caused alarm. People were not used to lights in the sky. They associated unusual phenomena with omens, with warnings from God. Red auroras, in particular, looked like blood in the sky, like fire, like the end of things. There are records from the 1500s of people fleeing their homes when the aurora appeared, believing the world was ending. Priests were called to pray. Bells were rung. The lights were seen as a sign of divine anger, of coming war or plague. And sometimes war did come. Sometimes plague did follow. But not because of the lights. The lights were simply there, indifferent and beautiful, while human history unfolded beneath them. In the winter of 1621, a French scientist named Pierre Gassendi saw the northern lights from Paris. This was unusual. The lights rarely traveled so far south. But that year, they did. Great shimmering curtains of red and white, rippling across the sky above the rooftops and the Seine. Gassendi watched them for hours. He was a careful man, someone who believed in observation over assumption. He wrote down what he saw, the colors, the movement, the way the lights seemed to pulse, and he gave them a name that would last. Aurora Borealis, the northern dawn. Aurora, after the Roman goddess of morning. Borealis, meaning northern. It was a poet's name, really, but it felt right. The lights did look like dawn, arriving in the wrong part of the sky. Gassendi did not know what caused the aurora, but he knew it was not vapors catching fire. The lights were too organized, too structured. They moved in patterns. They followed invisible lines across the sky. He suspected magnetism might be involved. The compass needle pointed north. The aurora appeared in the north. Perhaps there was a connection. He was closer than he knew. Still, no one knew what caused them. Not truly. The aurora remained a mystery, beautiful and unexplained, for another 200 years. The understanding began, as many things do, with something small, something almost invisible. In the late 1800s, scientists were experimenting with electricity. They had learned to create sparks, to send currents through wires, to make glass tubes glow with strange colored light. A man named William Crookes, working in London, built a glass tube with most of the air pumped out. When he sent electricity through it, the tube glowed with a soft, greenish light. He called the invisible stream inside the tube cathode rays. He did not know what they were, but he knew they carried energy. He knew they could make things glow. The glow was eerie and beautiful. It filled the tube with color that seemed to have no source. Other scientists built similar tubes, experimenting with different gases, different levels of vacuum. Each combination produced a different color. Neon glowed orange-red. Argon glowed violet. Helium glowed pink. It was like capturing pieces of the aurora in glass. Around the same time, other scientists were studying the sun. They had learned to split sunlight into its component colors using prisms. They had discovered that the sun was not just a source of light, but a source of many kinds of radiation. Some visible, some not. Spectroscopy, the study of light broken into its spectrum, revealed that different elements produced different patterns of color. Hydrogen had its signature. Helium had its signature. By looking at the light from the sun, scientists could tell what the sun was made of, even though it was 93 million miles away. This was astonishing. The idea that you could know the composition of something you could never touch, simply by looking at its light. The technique was simple in principle. Light passed through a prism or a diffraction grating, which separated the light into its component wavelengths. Each element, when heated or excited, emitted light at specific wavelengths. These wavelengths appeared as bright lines on a dark background, like a barcode. Each element had its own unique pattern. All sodium produced two bright yellow lines, very close together. Iron produced hundreds of lines, scattered across the spectrum. Hydrogen produced 4 distinct lines in the visible range: red, blue-green, blue, and violet. By comparing the spectrum of light from the sun to the spectra of known elements in the laboratory, scientists could identify what the sun contained. It was detective work, performed with light. A Norwegian scientist named Christian Birkeland connected these ideas. He was born in 1867, in a country where the aurora was part of the landscape, part of the rhythm of winter. He had watched the lights since childhood, and he wondered. Birkeland believed the aurora was electrical. He believed it had something to do with the sun. In his laboratory in Oslo, He built a small model, a magnetized sphere, meant to represent the Earth, a cathode ray tube, meant to represent the sun sending out particles. The sphere was called a terrella, a little Earth. It was painted with continents and oceans, and it sat in the center of a glass chamber. Birkeland could control the magnetic field around it, adjusting the strength and orientation. When he turned on the equipment, something remarkable happened. The particles from the cathode ray curved around the sphere, following the magnetic field lines, and concentrated near the poles. They glowed. It looked, in miniature, like the aurora. Birkeland published his results in 1908. He proposed that the sun was constantly sending out streams of charged particles, electrons and ions, invisible and fast. When these particles reached the Earth, they were captured by the planet's magnetic field and funneled toward the poles. There, high in the atmosphere, they collided with air molecules and made them glow. It was a beautiful theory, and it was correct, but the world was not quite ready to believe it. The idea of the sun sending out particles seemed too strange, too invisible. The sun was light and heat. The idea that it was also ejecting matter, constantly, into space. This seemed unlikely. Many scientists dismissed Birkeland's work. They preferred older theories. Atmospheric electricity, reflections of sunlight from ice crystals, anything but invisible particles streaming from the sun. Birkeland spent years trying to prove it. He traveled to the Arctic, setting up observation stations in the snow, measuring magnetic fields and auroral light. He endured brutal cold, equipment failures, isolation. He was driven by certainty. He knew he was right. He died in 1917 in a hotel room in Tokyo, far from home. His work was not widely accepted until decades later, when satellites finally detected the solar wind he had imagined. But the particles he imagined were real. They are still there, streaming out from the sun, every moment of every day. The sun is not a solid thing. It is a ball of plasma, hydrogen and helium, crushed together by gravity, burning at millions of degrees. At that temperature, atoms fall apart. Electrons are stripped away from their nuclei. What remains is a sea of charged particles, moving constantly, colliding, releasing energy. The core of the sun is where fusion happens. Hydrogen atoms are forced together under immense pressure and heat, forming helium and releasing energy. This energy works its way outward, taking thousands of years to travel from the core to the surface. By the time it reaches the surface, it has transformed many times, from gamma rays to X-rays to visible light. The surface of the sun, the photosphere, is cooler than the interior, only about 10,000 degrees Fahrenheit, cool enough that the light it emits is mostly visible to human eyes. But above the photosphere is the corona, the sun's atmosphere. And the corona is strange. It is hotter than the surface beneath it, much hotter, millions of degrees. Scientists still do not fully understand why. The corona should be cooler, not hotter. But magnetic fields bend and snap in the corona, releasing energy, heating the plasma to temperatures that seem impossible. Some of that energy escapes. Particles leap from the surface of the sun and pour out into space, carried by magnetic fields and heat. This stream is called the solar wind. It moves fast, more than 1 million miles per hour. It takes about 3 days to travel from the sun to the Earth, crossing 93 million miles of emptiness. The solar wind is thin. If you could hold a cubic inch of it in your hand, it would contain only a few dozen particles. But space is vast. and the stream is constant. So the total amount of matter flowing from the sun is enormous. The sun loses about 1 million tons of material every second. This has been happening for billions of years, and it will continue for billions more. When the solar wind reaches the Earth, it meets something invisible but very strong. The magnetosphere. The Earth, deep in its core, is made of iron, liquid iron, stirred by the planet's rotation. This motion creates a magnetic field, the same kind of field that makes a compass needle point north. But the Earth's magnetic field is enormous. It extends thousands of miles into space, wrapping the planet in a protective bubble. The magnetosphere is shaped like a teardrop. On the side facing the sun, it is compressed by the solar wind, pushed inward. On the side facing away from the sun, it stretches out into a long tail, millions of miles into space. The solar wind presses against this bubble. Most of the charged particles are deflected, pushed aside, sent streaming past the Earth like water flowing around a stone in a river. But some particles slip through. They follow the magnetic field lines, spiraling down toward the poles, north and south. The places where the field lines converge, where the magnetic forces are strongest. The particles do not fall straight down. They spiral. They follow the curves of the magnetic field, moving in tight helixes, drawn inexorably toward the poles. And there, very high in the atmosphere, something beautiful happens. The atmosphere, at that altitude, is thin, about 60 miles up, far above the clouds, far above the weather. The air is mostly oxygen and nitrogen, the same elements that you breathe, but spread so thinly that a handful of it would feel like nothing. At sea level, the atmosphere is dense. Molecules are packed tightly together. But as you rise, the air thins. At 60 miles, the pressure is less than 1/millionth of what it is at sea level. The air is almost vacuum, almost space. But not quite. There are still molecules there. Still atoms of oxygen and nitrogen, drifting slowly in the dark. When a charged particle from the solar wind collides with an oxygen molecule, it transfers energy. The oxygen molecule absorbs that energy, and for a brief moment, it becomes excited, unstable. It cannot hold that much energy for long, so it releases the energy as light. Oxygen, when it releases energy in this way, glows green, a soft, pale green, the color of new leaves in spring. This is the most common color of the aurora, the color that appears in most photographs, most paintings, most memories. The green light comes from oxygen atoms at an altitude of about 60 to 150 miles. This is where the collisions are most frequent, where the density of the atmosphere is just right. Sometimes, if the collision happens higher in the atmosphere, where the oxygen is even thinner, the light is red instead. A deep, dusky red, like embers. Red auroras are rarer. They require more energy, higher altitudes, specific conditions. But when they appear, they fill the sky with a color that feels ancient, primal. Nitrogen glows differently, blue or violet, depending on how the energy is released. Nitrogen light is rarer, but when it appears, it adds depth to the aurora. Layers of color shifting behind the green. Blue light comes from nitrogen molecules that are ionized, stripped of an electron. Violet light comes from neutral nitrogen, still whole. The difference is subtle, but it is there, written in the wavelengths of light. The colors are not painted. They are not projected. They are simply the way those particular atoms release energy. The same process that makes a neon sign glow, or a firefly's abdomen shine. Chemistry, translated into light. And because the charged particles are always moving, always spiraling along the magnetic field lines, the light moves too. It ripples, it pulses, it forms curtains that seem to blow in a wind that does not exist. The shapes of the aurora are determined by the magnetic field. The particles follow the field lines, and the field lines curve and converge. Where the field lines are vertical, the aurora appears as rays, sharp lines of light pointing upward. Where the field lines are horizontal, the aurora appears as arcs, smooth curves stretching across the sky. Sometimes the aurora forms a corona, a crown of light directly overhead. This happens when you are standing beneath the point where the magnetic field lines converge. The rays appear to radiate from a central point, like spokes on a wheel. The aurora is not solid. It is not a surface. If you were standing beneath it, and you could somehow rise up through the atmosphere, you would pass through the light and feel nothing. It would surround you, and you would be part of it, and it would still be nothing but air and energy. But from the ground, on a cold, clear night, it looks like magic. The best place to see the aurora is inside the auroral oval. This is a ring-shaped region that circles each magnetic pole, about 10 to 20 degrees away from the pole itself. It shifts slightly, depending on the strength of the solar wind, but it is always there, an invisible boundary where the charged particles are most concentrated. Northern Norway sits inside the auroral oval. So does northern Sweden, northern Finland, Iceland, Greenland, northern Canada, and Alaska. These are the places where the aurora appears most often, sometimes dozens of times each winter. The city of Tromsø in Norway is one of the best places in the world to see the aurora. It sits at 70 degrees north latitude, well inside the auroral oval. The city is small, built on an island, surrounded by mountains and fjords. In winter, the sun does not rise for 2 months. The polar night. During the polar night, the sky is dark all day. Not completely dark. There is a faint twilight around midday, a glow on the southern horizon, where the sun is just below the edge of the world, but dark enough for stars, dark enough for the aurora. The people who live in Tromsø have adapted to the darkness. They light candles in their windows. They gather in cafes where the light is warm and golden. They go about their lives in a kind of perpetual evening, neither day nor night, but something in between. The lights are strongest during the long polar night, when the sun does not rise for weeks or months. The sky stays dark, and the stars are visible all day. And if the solar wind is active, the aurora can last for hours. People who live in these places grow accustomed to it. They glance up, see the lights beginning, and go about their evening. It becomes part of the landscape, like the snow, like the cold. But for visitors, it is different. There is something about seeing the aurora for the first time that stays with you. The silence of it, perhaps. The way it moves without sound. The sense that you are watching something vast and distant. Something that has been happening long before you arrived and will continue long after you leave. The aurora is silent. This surprises people. They expect sound. The lights are so vivid, so dynamic, that it seems like they should make noise. A hum, a crackle, a whisper. But there is no sound. The aurora happens too high, in air too thin to carry sound waves. Even if the collisions between particles and air molecules did produce sound, it would dissipate long before reaching the ground. And yet, some people insist they have heard the aurora, a faint crackling, like static. a rustling, like silk. Scientists have investigated this. The sounds, when they occur, seem to be real, but they do not come from the aurora itself. They come from the ground. During intense auroral displays, the electric fields can be strong enough to cause small discharges from objects on the ground, trees, buildings, even hair. These discharges produce faint, crackling sounds. So in a way, the aurora does make sound, just not in the way people expect. The silence, though, is part of the experience. Standing in the snow, watching the sky fill with light, and hearing nothing. Only the wind, perhaps. Only your own breathing. The silence makes it feel more vast, more distant, more like something happening in another realm. Scientists began to study the aurora more carefully in the 20th century. They built instruments to measure the magnetic fields, the particle densities, the wavelengths of light. They sent rockets into the upper atmosphere to sample the air where the aurora occurred. They launched satellites to observe the sun and the solar wind. In 1958, a scientist named James Van Allen discovered something unexpected. The Earth's magnetosphere was not empty. It contained belts of trapped radiation, regions where charged particles were held in place by the magnetic field, circling the planet over and over. These belts were named after him. The Van Allen belt. There are two main belts. An inner belt, about 400 to 6,000 miles above the Earth's surface, filled mostly with protons, and an outer belt, about 8,000 to 36,000 miles up, filled mostly with electrons. The particles in these belts are trapped. They bounce back and forth between the northern and southern hemispheres, spiraling along the magnetic field lines, never escaping. Some of them have been there for years. The aurora, it turned out, was connected to these belts. When the solar wind was particularly strong, particles from the belts were shaken loose and funneled down into the atmosphere. The aurora brightened. The colors intensified. This happened most often during solar storms. The sun, every 11 years or so, goes through a cycle of activity. During solar maximum, the surface of the sun is covered in dark spots, regions of intense magnetic activity. Flares erupt. Plasma is ejected into space in great looping arcs. The solar wind becomes faster, denser, more chaotic. Sunspots are cooler than the surrounding surface, which is why they appear dark. But they are centers of magnetic activity. The magnetic field lines bend and tangle, storing energy. When the field lines snap and reconnect, they release that energy in sudden bursts. Solar flares are explosions of light and radiation. They happen in minutes. The light reaches Earth in 8 minutes, traveling at the speed of light. Coronal mass ejections are different. They are eruptions of plasma, billions of tons of charged particles hurled into space. They travel slower than light, but they carry more mass, more energy. When they reach Earth, they can cause geomagnetic storms. When one of these storms reaches the Earth, the magnetosphere shudders. The auroral ovals expand. Lights that are normally confined to the Arctic appear much farther south. In 1859, during the largest solar storm ever recorded, the aurora was visible as far south as Cuba. Telegraph wires sparked and caught fire. Compasses spun uselessly. It was called the Carrington event, after the astronomer who observed the solar flare that caused it. Richard Carrington was observing the sun through a telescope when he saw a bright flash on the sun's surface. He sketched it quickly, not knowing what it meant. 17 hours later, the aurora appeared. Red and green and white, visible across most of the planet. People in Boston could read newspapers by the light of the aurora at midnight. Miners in the Rocky Mountains woke up and started making breakfast, thinking it was dawn. If a storm like that happened today, it would disrupt satellites, power grids, communication systems. But in 1859, it was simply beautiful and strange. The people who saw it did not know what it meant. They stood in their fields and on their rooftops, watching the sky turn red and green, and they wondered. The aurora appears in the south as well. The Aurora Australis, the southern lights. They follow the same process, the same physics, the same magnetic field lines, but fewer people see them because the southern auroral oval circles Antarctica, where almost no one lives. The Aurora Australis is just as beautiful as the Aurora Borealis. The same colors, the same movements, the same silent glow. But it happens over ice and empty ocean, far from cities, far from observers. Scientists who work at research stations in Antarctica sometimes see the Aurora Australis on clear winter nights. It stretches across the sky above the ice, reflected in the snow, doubling itself. Green above, green below, and the observer standing in between. There is something humbling about it, the sense of being very small on a very large planet, beneath a process that involves the sun and the magnetosphere and the thin skin of the atmosphere. All of it indifferent to you, all of it continuing. The aurora does not need to be watched. It does not need to be understood. It simply is. But we watch anyway. We try to understand, because that is what we do. In recent years, photographers have traveled to the Arctic in winter, hoping to capture the aurora. They set up cameras on tripods in the snow, long exposures, wide lenses. The photographs are stunning. The colors are often more vivid than what the human eye can see, because the camera can gather light over time, accumulating photons that the eye would miss. A camera sensor, left open for 10 or 20 seconds, can collect enough light to reveal details invisible to the eye. The faint red glow at high altitude, the subtle violet fringes, the structure within the green curtains. But even in person, even with the naked eye, the aurora is worth the cold, worth the waiting, worth the darkness. The experience of standing beneath the aurora is difficult to describe. It is not just visual, it is spatial. The lights fill the entire sky, from horizon to horizon. They are above you, around you, moving in 3 dimensions. You feel small beneath them, small and quiet. Some people say it looks like fire. Some say it looks like water. Some say it looks like silk or smoke or breath. All of these are true, and none of them are quite right. It looks like light, moving through air. That is all it is. That is enough. The science of the aurora is settled now. We know where the particles come from. We know how they travel. We know why they glow. The mystery is solved. Spacecraft have flown through the aurora, measuring the particles directly. Satellites monitor the solar wind constantly, predicting when auroras will occur. Cameras on the International Space Station have photographed the aurora from above, showing the full extent of the auroral oval, a glowing ring around each pole. From space, the aurora looks different, thinner, more delicate. A faint green glow on the dark side of the planet, like bioluminescence in the ocean. The astronauts aboard the station sometimes watch the aurora from their windows. They see it spread out beneath them, a glowing band wrapped around the pole. They see the structure that is invisible from the ground, the way the aurora follows the magnetic field lines, the way it pulses in waves, the the way it responds to changes in the solar wind. From that height, the aurora is peaceful. Silent, of course, but also still. The motion that seems so dramatic from the ground is gentler from above. The lights shift slowly, like oil on water, forming patterns that dissolve and reform, but the aurora itself has not changed. It still appears in the Arctic night, green and violet and rose. It still moves in silence. It still feels, when you stand beneath it, like something more than physics. The Sami people, who named it long ago, were not wrong. It does feel like spirits, like something alive, not because it is, but because we are, and we see ourselves in everything. The aurora has been appearing for as long as the Earth has had a magnetic field and an atmosphere. Billions of years. Long before there were eyes to see it. Long before there were minds to wonder about it. Dinosaurs walked beneath the aurora. Early mammals, small and nocturnal, saw it glowing above the ancient forest. The first humans, stepping out of Africa, looked up and saw the lights in the northern sky. And they told stories. They made sense of it the best way they could, with foxes and spirits and herring beneath the ice. The stories were not wrong. They were just different ways of knowing. Now we have another way. We have particles and magnetic fields and spectroscopy. We have satellites and equations and models. We can predict the aurora. We can measure it. We can explain it. But the aurora does not care. It continues, indifferent to our understanding. And perhaps that is the most beautiful thing about it. The aurora is not for us. It is not a message. It is not a sign. It is simply a consequence of the sun and the earth and the space between them. We are fortunate to be here, on a planet with a magnetic field, with an atmosphere, with eyes that can see the light. We are fortunate to live in a time when we can travel north, stand in the snow, and watch. The sky is very dark now. The lights are fading, the way they always do. The green curtains thinning, becoming translucent, becoming suggestion. The charged particles, high above, are slowing. The collisions are fewer. The oxygen molecules return to their quiet state, releasing no more light. The aurora does not end. It simply stops being visible. The sky returns to stars. The same stars that were there before, patient and unchanging. Constellations that people have watched for thousands of years, connecting the dots into shapes that meant something. A bear, a hunter, a river. The stars are farther away than the aurora, much farther. The nearest star, other than the sun, is more than 4 light years away. The light you see from it left that star 4 years ago, traveling through empty space at 186,000 miles per second, and it is only just now reaching your eyes. The aurora, by comparison, is close, only 60 miles up, close enough to touch almost, close enough to feel part of the Earth rather than part of space. But it connects them, the Earth and the sun and the space between. It makes visible something that is usually invisible, the constant stream of particles, the magnetic field, the thin atmosphere that glows when touched by energy from 93 million miles away. Somewhere, the solar wind continues. Somewhere, the magnetosphere holds steady. Somewhere, the Earth turns, and the night moves on. And you are here, beneath the blanket, beneath the quiet. The room is warm. Your breathing is slow. There's nothing left to see, nothing left to know. Only rest now. Only the soft weight of sleep, settling in like snow. The lights were beautiful. They always are. And they will be there tomorrow, and the night after, and the night after that, glowing in the dark, waiting for no one. Perfect